In a reentrancy hack, a contract will call a target contract. This target contract will call back into the caller, in this case the hack contract. Well, the first call has now finished, this hack contract will call back into the target contract. This is reentrancy hack. A read-only reentrancy is a little bit more complicated. First, the hack contract will call into a contract. We'll call this contract A. Contract A will call back into the caller. In this case, it will be the hack contract. At this moment, the call made in the first step to contract A has not yet finished. While the call in the first step is not yet finished, this hack contract will call into a target contract. The target contract will read some state from contract A, finish executing step 3, after the function call to the target contract finishes, then the execution to step 2 finishes, and lastly the execution to step 1 finishes. Let's take a look at an example. For this example, I'll be using Foundry, so first let's install it. I'll install Foundry by copying and pasting this command into my terminal. All of the command and the codes that I'll be typing, I'll put it up on GitHub. The next step of installing Foundry is to type Foundry up. So I'll type Foundry up. Next, I'll initialize a Foundry project inside this directory by typing forge init. Okay, once that command executed successfully, if I check the current directory, you can see some files that Foundry put in. And we're now ready to write some code for the read-only reentrancy example. For this example, we'll simulate a read-only reentrancy attack on the curb STEF pool. And we'll be executing this on the mainnet fork. So we won't be actually hacking the contract, we will just be running a simulation. First, I'll open source folder and then remove this boilerplate code. And then I'll create a new contract called hack.sol. First, I'll paste the Solidity version. Next, I'll import console.sol so that we'll be able to console log some values inside the transaction. Next, I'll set the address for the curb STEF pool and the token that you get when you deposit into this pool. I'll name it LP for liquidity provider. We're going to be hacking the curb contract, so I'll paste the interface for the curb. For this example, the functions that we're going to be calling is get virtual price, add liquidity, and remove liquidity. When you call this function get virtual price, it returns the value of the shares. The higher the value of the shares, the more tokens that you'll get that is locked inside the pool when you call the function withdraw. We can add the tokens to this curb pool by calling the function add liquidity, and to remove the tokens from this pool, we'll be calling the function remove liquidity. We're also going to need the IERC20 interface, so I'll paste it here. Okay, so next, let's write the hack contract. So I'll type contract hack. First, let's set some contract addresses. iCurb, this will be private, constant, and I'll name it pool, and this is equal to iCurb. This is the interface that we defined above, and the address of the pool that we'll be calling is STEF pool. I'll also set the IERC20 for the LP tokens, so IERC20 private constant LP token, and this will be IERC20 for the LP. This is the token that we'll receive when we call the function add liquidity on the curb pool. Next, I'll write the function called pong. This will be external and payable since we will be sending some ETH. This will be the main function that we'll be calling to initiate the attack. So what we're going to be doing is to first add liquidity to the curb pool. Next, we'll log the value of the shares by calling the function get virtual price. Log get virtual price. And then we'll remove liquidity. By calling this function, we'll be able to trigger the read-only reentrancy attack. When we call the function remove liquidity on the curb STEF pool, and then if I scroll down, you can see here that it sends the ETH back before the function finishes executing. So this means that when we call the function remove liquidity, the code will execute, and then before it finishes executing all of the code, it will send some ETH. So this is where we can do the reentrancy. Back inside my code editor and back inside our contract, when we call the function remove liquidity, at some point it would send the ETH back to this contract. So inside this contract, I'll define a receive, external, payable, and this is where we will write our rest of our code to execute the read-only reentrancy. In this example, to show you that get virtual price will be higher while we're still executing remove liquidity, inside here, we'll log get virtual price again. Okay, let's write our code. The first thing is to add liquidity. Now, if I scroll up to call add liquidity on the curve pool, we'll need to prepare an array of 2 specifying the amount of tokens to add and the minimum amount of LP tokens to mint. So, scroll down. First, we'll initialize a uint array of 2, uint 2, memory, I'll call it amounts, and this will be equal to, the first value represents the amount of ETH that we're going to be sending. So we'll be sending message.value. The second amount represents the amount of ST ETH that we're sending. We'll be sending 0. And then we'll add liquidity by calling pool.addLiquidity, passing in the amounts and the minimum amount of LPs that we'll be minting. We'll say 1. And when we call this function addLiquidity, since this is a ETH ST ETH pool, we'll have to also send the amount of ETH that is specified over here. So say value is message.value. When we call this function addLiquidity, it returns the amount of LP tokens that were minted. So I'll say uint LP equals to, and that is addLiquidity. Next, we'll log the virtual price, the value of 1 share of these LP tokens. So I'll say console.log, and then I'll type before remove LP virtual price, and then call the function pool.getVirtualPrice. And then we'll remove liquidity. Let's scroll up. To call remove liquidity, we'll need to pass in the amount of LP tokens that we're going to be burning and the minimum amount of underlying token. This will be ETH and ST ETH that we expect to receive. So scroll down. We'll prepare a uint array of size 2, uint 2, memory, min amounts. For this example, I'll just say minimum amounts are 0, uint 0, uint 0. And then we'll call the function remove pool.remove liquidity, passing in the amount of LP tokens that we're going to be burning. We'll withdraw all of it, so we'll pass in all of our LP tokens and pass in minimum amounts. When we call this function remove liquidity, at some point it will send us back the ETH, which will trigger the receive function. So inside here, we'll log the get virtual price. So I'll copy this, paste it here, and then say during remove liquidity, log the virtual price. Okay, this completes the first step of our hack contract. What we're trying to see here is that while we're calling remove liquidity, we should see that get virtual price is higher. And by confirming that get virtual price will be higher while this part of the function is executing, we'll be able to write our exploit inside this receive function. So let's first check that get virtual price is actually higher inside this part of the code. So I'll open my terminal, and then I'll try to compile the contract by typing forge build. Now I noticed that the contract didn't compile because there was a contract in the test file that we deleted. So I'll go fix that right now. Open the test, and then remove the imports, and then remove all of the code inside the test. And let's try compiling again. Okay, our contract compiles. Let's now write the test. I'll rename counter to hack.t.sol, and also rename the test contract to hack test. Instead of importing the counter, we'll import the hack contract. And then inside our test contract, I'll also import the console from forge.std. So I'll copy this, paste it here. And then first we'll initialize the hack contract. So I'll type hack public hack, and then we'll write the function to set up the test. Function set up public, and then we'll initialize the hack contract. Hack is equal to new hack. Next, we'll write a function to test our pwn function. Function test pwn public, and then we'll call the function hack.pwn. When we call this function, let's send 100,000 ETH. So I'll say value 100,000 times 1E18. Okay, let's execute the test. So when we call the function pwn, we should see that get virtual price will be higher inside the receive function compared to what we get when we call the function get virtual price inside the pwn. So I'll open my terminal, clear the logs, and then we'll be running our test on the mainnet fork. So I'll copy the address for the fork URL that I got from Alchemy API. I'll paste this command, sending the fork URL to the Alchemy API. And then we'll execute the test by calling forge test dash. I'll put in 4 B's, B, and this will print out a lot of logs when we run the test. And then we'll say fork URL is fork URL from what we set above, and then hit enter. Okay, our test finished executing, and you can see that there is a lot of logs. This is because if I scroll up, I put in 4 B's, and this means that it will print a lot of logs. For this execution, what I am interested in is in the virtual price before removing liquidity and the virtual price during removing liquidity. Let's take a look. Before removing liquidity, it is this amount that you see over here. And when we're removing liquidity, you can see that the virtual price has gone up by a little bit. You see a 5 over here, and you see a 9 over here. What this means is that if we target another contract that depends on virtual price and then call that contract while we're removing liquidity, we'll be able to exploit that contract. That will be the next step. Okay, I'm back in my hack contract, and what we're going to do next is write an example contract to target a contract to exploit inside the function receive. So first, I'll write a target contract that we'll be using for this example. So I'll say contract target, and let's imagine that this target contract, you'll be able to stake the LP tokens and you'll get some kind of rewards where the rewards is calculated based on the value returned by get virtual price. So first I'll copy these two contract addresses, and instead of LP token, here I'll name it token. I'll rename it to token. So let's imagine that this contract has 3 functions. A function to stake the tokens, a function to unstake the LP tokens, and some kind of function to get rewards based on the amount of tokens that we stake. Function get reward. Okay, let's fill in the details. So stake, it will take in the amount of LP tokens to stake. This will be external. And when we call this function, let's say that it transfers the token, transfer from message.sender to this contract address. This for the amount from the input. And then let's say that it keeps track of the amount of tokens that is staked. So I'll create a mapping from address to uint. This will be public. I'll name it balance up. Then when we stake, it will update the balance of for message.sender incremented by amount. Okay, scrolling down. When we unstake, we'll be able to unstake the amount. This will be external. When we unstake, we'll first update the balance of message.sender decremented by amount, and then we'll transfer the token. Token.transfer to message.sender for the amount. Okay, the last function we'll write is get rewards. So this will be external. Returns, let's say that it just returns the amount of rewards tokens that we earn. We'll say that the amount of rewards token that we earn is we multiply the amount of stake by the value of shares, and the value of shares we get it by calling get virtual price on the curve pool. So say uint reward is equal to balance of message.sender times get virtual price pool.get virtual price. Now both the LP tokens and get virtual price has 18 decimals, so what we'll have to do is divide by 10 to the 18. If we multiply balance of, which has 18 decimals, and get virtual price, which has 18 decimals, this multiplication now has 36 decimals. So to get it back down to 18 decimals again, we'll have to divide by 10 to the 18. And then we'll have some code to transfer the reward, but for this example, we'll just omit it. Skip code to transfer reward, and for this example, we'll just return the amount of reward that was calculated. Okay, let's try compiling this contract. Clear the logs, and then type forge build. Okay, the contract compiled successfully, so let's move on to write some exploit inside the hack contract. So, scrolling down to the hack contract, first I'll store the target contract inside the hack contract. So I'll say target private immutable target, and then define a constructor. Constructor will take in the address of the target, and then we'll set the target equal to target address of target. Now what we're going to do is, before we call the function pwn, we'll stake some LP tokens into the target contract, and then afterwards we call the function pwn. This will eventually call remove liquidity, which will call the receive function. Inside here we know that get virtual price is overpriced, so inside here we'll call the function get reward on target, and we should get more rewards than what we should have if we didn't do the exploit. Okay, so let's do that. So first I'll create a function called setup. This will be external payable, and inside here we'll stake some tokens into the target contract. So first we'll need to add liquidity. Copy this, paste it here, and then we'll transfer this LP token over to the target contract. So LP token dot approve address of the target for the amount LP, and then call target dot stake LP. Next, we'll execute the pwn function, and this will execute remove liquidity, which will execute receive. And inside here, let's get the reward by calling uint reward is equal to target dot get reward. And then for this example, we'll log the amount of rewards that we earned if we had called get reward inside the receive function. So say console.log reward. And then we'll also compare this amount of rewards that we would have got, compare it to how much reward we will get if we called it after the read-only reentrancy is done. So if we did not execute a read-only reentrancy, how much reward will we get? I'll copy these two code and then paste it here. Okay, let's update our test. So back inside the hack test contract, I know that we'll need to deploy the target contract. So target public target, and then we'll deploy the target contract first. Target is equal to new target. And now the hack contract takes in the address of the target. So inside the constructor, I'll pass in the address of the target. And then before we call the function pwn, we'll need to call the function setup to stake some of our LP tokens into the target contract. So here, hack.setup. And when we call this function setup, we'll get some LP tokens from the pool, from the curb_st ETH pool, and then stake it. So let's send some ETH. So I'll say value, we'll send 10 ETH, 10 times 10 to the 18. Okay, let's try compiling the contract. I'll open the terminal, clear the logs, and then type forge build. And our contract compiles. So let's now run the test again. And our test was successful. Let's check the logs. Scroll up. Before we remove liquidity, get virtual price, return some amount. During the LP is being removed, so this will be the code that was executed inside the receive function. Get virtual price was slightly higher, and when we call the function get reward, we would have gotten this much amount, whereas after remove liquidity is done executing, and then we call get reward, we get a slightly less amount. This means that if we were to call get reward while the liquidity was being removed, then we would have gotten more rewards than calling get reward after we called remove liquidity. That was an example of read-only reentrancy where we wrote our hack contract, and then we called the curb_st ETH pool. We called it by calling the function remove liquidity. And then while the remove liquidity is executing, it transferred some ETH. And then inside here, it executed the code inside the receive, which allowed us to call the target contract get reward. Get reward calculated the amount of rewards by calling get virtual price inside the curb pool. At this point, the virtual price is slightly higher than what it should be. So By the time all of this finished executing, we were able to get more rewards than what we would have if we did not execute the read-only reentrancy.